The whole point, well, I'm not gonna say the whole point. Okay, we're hitting into something where I know students get caught in the weeds and they get stuck, and it's just, and I can feel their frustrations, and it's kind of stressful for all of us. But my hope is that I can kind of negate a little bit of that with this and the way I'm going to explain it. So, what we're getting into now is something called valence bond theory, and we're going to dive into orbitals. Okay. And I know orbitals are a sticky point for a lot of people. But what I really want us to get into is just to, I'm not going for a deep philosophical understanding of quantum mechanics. Okay. This is something that we're going to come back to over and over again. And as you go further in your career, you will get more knowledge about the intimate details of orbitals. Okay. My goal with valence bond theory is two things. We're going to cover one of them in this video and one of them in the next video. But one of those is to find the link between electronic geometry and the orbitals involved in the molecule, because those two things are together, and uh, we're going to have a chicken and the egg argument in a minute here, but it doesn't matter. Those two things are intimately connected. Okay. And the other thing is it's going to give us a way to look at the bonds in molecules, and we'll hit that one in the next video. All right. So valence bond theory was put out by Linus Pauling. This is Linus Pauling here. The same guy that did the electronegativity scale, all that fun stuff. Essentially, what we're saying here is this is a mathematical combination of wave functions. And this is where, whatever. I say that to scare us. It's fine. We're not going to do any math. We're just going to look at pictures and try to think about geometry. Okay. All right. So for valence bond theory to work, there's kind of two thoughts for valence bond theory. One is you're going to form a covalent bond when orbitals overlap. And all that means is the two orbitals are occupying the same space, so the electrons can share the volume of space where they are. Okay. Once the orbitals overlap, there's a maximum of 2 electrons in the overlapping orbitals. Okay. Which means either each orbital came in with 1 electron, or one orbital had 2 and the other orbital had none, but whatever, we need to have 2 electrons max. Okay. And they're spin paired. What do we mean by spin paired? We're talking about, one going up and one going down, just when we talked about electron configurations and all that stuff. Okay. We're focusing in on valence electrons, and we're trying to remember, right? We're forming covalent bonds because this is a lower energy or more stable situation. Okay. Let's start off with hydrogen. If we're thinking about taking hydrogen, and I don't know if you can see my hands, but I'm a hand talker. The two hydrogen atoms at an infinite distance roughly have an energy of 0 because they're not really interacting with each other. Okay. As the two hydrogen atoms get closer and closer together, the energy goes down because they're starting to share. And when they're sharing, they're fulfilling their version of the octet rule, right? Everybody has the right number of electrons that they want, and this is a lower energy situation. At some point here, they're at an ideal distance where the electrons are equally shared, the nuclei are happy, and everybody's okay. All right. If you keep trying to shove those orbitals together, then the nuclei start realizing that the nucleus is there and they start repelling each other. And this is a horrible situation, and the energy flares up. Okay. Remember, our goal here is to think about how the overlapping orbitals are tied to the geometry of the molecule. That's my whole goal with valence bond theory, you guys. Okay. So let's look at some examples here. If we look at an HF molecule, remember hydrogen this is a hydrogen with a 1s, configuration, right? So we have a spherical orbital. Fluorine is 2p5, has 1 spot open for a valence electron, and so the hydrogen shares 1 with it, and they overlap, and you can easily see there's a bond right there. Okay. This top one is fluorine overlapping with himself to make a single bond right there. Okay, makes sense. If we look at H2S, it's the same idea. We have hydrogens. Sulfur has 2 unpaired electrons, and so they can overlap with a hydrogen there, they can overlap with a hydrogen there, and we have H2S that looks something like this. This makes sense, okay? And it follows what we know about orbitals. This is all valence bond theory here, okay? Nothing too super crazy, okay? Now, if we do the same idea and we apply it to carbon, what we predict is, right, we have two unpaired electrons, so each hydrogen will bond once. This will look a lot like H2S. We'll have a 90-degree angle, and that's fine. However, what we see in reality is we get methane, we get CH4, and we have something tetrahedral with these angles being 109.5 degrees. And this does not mesh well with the picture of how we've been doing orbitals up to now. Okay, so there has to be something else happening with these things to make methane look the way it does. Okay, what's happening is something called hybridization. And in hybridization, we're really doing two things. We're saying, okay, if we want to have four, right, for methane, we need to have four CH bonds. Okay, so we need to have carbon with having four unpaired electrons. And so it does what's called a promotion. And one of these S electrons gets promoted to be a P electron. And now we have four singly occupied atomic orbitals. Okay, the other thing is all four of those CH bonds are exactly the same. Okay, if we overlap an S and a P, it's going to look not the same as overlapping a S and an S. Okay, so what happens in the second part of this is hybridization, and the atoms just do this. Okay, it takes the four atomic orbitals that each have one valence electron and mixes them all together and splits them back up equally so that we have four hybrid orbitals. Okay, the hybrid orbitals we have are called sp3 when we do this. Okay, they're called sp3 because there's an S, a P, a P, a P, and they make sp3. Okay, and there's four identical sp3 orbitals, and it makes things nice and look tetrahedral. Okay, so our link here is the geometry. Okay, notice we're counting things by electron groups. So if you have four electron groups, right, you need four identical orbitals. I should be writing this down. Okay, four, I didn't want yellow. Okay, four electron groups, which means we need four identical orbitals, which means we're going to be sp3. And sp3 and tetrahedral go together. Remember, this is thinking about the electronic geometry. sp3, tetrahedral electronic geometry go together. Okay, which means if we're looking at ammonia, it is the same situation. That is tetrahedral electronic geometry, even though it's trigonal pyramidal shape. Okay, it's doing the same steps. Well, kind of not, it doesn't have to do the promotion step, but we're mixing together the S and the P. We're getting four sp3 orbitals. One of them is already full. Okay, so if we're looking at this from a valence bond perspective, we can say, oh, this guy's already full. So this is our lone pair. These ones are singly occupied. So those are free to overlap with hydrogens. And we have three NH bonds and we have a lone pair. Okay, you would get the same thing with water, which I don't think I have water here. No. Okay. So that's sp3. Remember, sp3 tetrahedral electronic geometry. Okay. Now, we have three electron groups, right? Here we'll look at BF3 or boron trifluoride. It's going to do kind of the same idea. We're going to promote one of these boron electrons from an S to a P. So we have all unpaired electrons. Okay. And then we're going to combine them together. If we have three electron groups, then we need three orbitals. And that's going to be sp2 because there's an S, a P, and a P. And if we add those together, we get sp2. Okay, there's three things there. The names of the hybrid orbitals match the orbitals they're made out of. Okay. The other thing we can think of here is that when we're making hybrid orbitals, the number of orbitals that we put into the mix is the same as the number of hybrid orbitals we get out. So you'll notice in boron, we've mixed together 3 atomic orbitals. We get 3 hybrid orbitals back out, and we're left with this empty, unhybridized p orbital left over. This orbital is important, and we'll get to that later. Okay, so there's that unhybridized p orbital. You can see we can overlap borons and fluorines this way, and we have trigonal planar, and this is all hunky-dory. Okay, if we have 2 electron groups, this is beryllium dichloride, BeCl2. It's the same idea, except now we have 1 less electron. So one of these electrons gets promoted up. Okay, we're going to mix together 2 orbitals to get 2 sp orbitals out. Remember, so 2 electron groups. We need 2 orbitals, and that's going to be sp2. Okay, remember 2 electron groups is going to be linear. And when we look at this, our sp orbitals are 180 degrees away from each other. These white ones here are unhybridized leftover p orbitals, and those are going to be important for us later too. So sp means we have an s and a p to give us sp. Okay, this view here is showing us 2 sp orbitals at the same time, which is what we would have here with the beryllium-2 at the same time. And each one of those will overlap with a chlorine like so, and we have a nice linear thing. So these guys are going to be linear. Okay, remembering our goal here is to link geometry and the hybrid orbitals. Okay, which means we have other geometry still to talk about. But while I'm thinking about it, I want to say that our secret word for this is acid storm. Acid storm. So do with that what you will, what you need to do with that. Yeah. So we talked about 4. We talked about 3. We've talked about 2. Remember, if we have more than 8 electrons, we have different geometries. And so with 5, right, we can have PCl5, phosphorus pentachloride, and it does the same idea. Promote 1 up. Now, we don't have 5 orbitals between s's and p's. To get the 5 orbitals, remember, if we have 5 electron groups, then we're going to need 5 orbitals, which means we're going to need an s, a p, a p, a p, and a d. Okay, this is also why things in period 3 and higher are the only ones that can have more than 8 valence electrons, because you have to have access to this d orbital, and things in period 2 are too remote from having the d orbitals, and so you get that first d from the period 3. Okay, so again, the phosphorus mixes together, it's 5 orbitals. We get 5 sp3d orbitals, and all of these together are the trigonal bipyramidal. What is with my spelling? I'm sorry. Trigonal bipyramidal. Okay, and we have formed 5 covalent bonds to the phosphorus and chlorines, and it has the right geometry when we think about it. Okay, one last one. Let's talk about sulfur hexafluoride. This is 6 electron groups. 6 electron groups means we're going to need 6 orbitals. And so we're going to have s, we're going to have 3 p orbitals, and we're going to have 2 d orbitals. So we're going to get sp3d2, and these guys are going to be octahedral. Okay, the geometry and the hybrid orbitals go together. Okay, so all of these octahedral sp3, I don't know why this isn't labeled on the thing, but sp3d2 orbitals line up and give us a covalent bond between the fluorines and the sulfurs, like so. And the octahedral geometry is there because the geometry is there in the orbitals. Okay, so the hybrid orbitals set up the central atom to be the geometry that we know it to be. Okay, so this is our critical understanding and what I have to try to impress upon us here as we do this. Okay, your number of electron groups tells us the geometry. And now it also tells us the hybrid orbitals, and these are married together. 2 electron groups is sp, which is linear, 4 is sp3 is tetrahedral, and so on and so on. So all of these link together. Okay. If you can figure out what the geometry is, then you know the hybridization of the central atom because they go together. Okay. So there's a lot going on in the valence bond theory. I just want us to know things. So, of course, I want you to know things, but uh, this is what I expect, right? For hybrid orbitals, we need to be able to recognize what the orbitals are. If I show you a picture, which is likely one of the ones that you've seen in this video, because those are my stock sets of pictures. If I show you a picture, you should be able to tell me what orbitals those are. Okay. You should be able to link the orbitals to the geometry. Okay. Which is how you're going to identify the hybridization of an atom in a Lewis structure. Okay. So if I give you a big Lewis structure picture and say, okay, what's the hybridization on this atom right here? You should be able to tell me, oh, well, that's got 4 electron groups on it, so it's got to be tetrahedral. Okay. Um, if you need anything else, let me know. Okay. I'll come back with our second part of valence bond theory in a moment. That will cover up my second thing to talk about with that. Okay. If you need me, let me know. I'm here and I'll catch you later.